So I show you all this stuff about Venus because it's really, really an important end member for how big rocky planets work. And some scientists at one point thought that all these mountain areas on Venus were like the mountain ridges of the ocean floor. And Venus is ripping itself apart and exuding energy through these chasmata, these canyons or chasms, the way the mid-ocean ridges do on Earth. Now, maybe some of you have thought about mid-ocean ridges. I think it's important to say that our planet regulates its internal heat balance by a system of 45,000 kilometers of mid-ocean ridges, which come on land in Iceland, a little bit in Africa, and we see the hotspot traces of them in Hawaii and other places. If we did not have that system, our planet would be a lot hotter. The crust would have to conduct more of the energy of this big hot interior. That's not good. Would not be as good a place to live. Well, here we have an area, the United States would fit right here. Here we have an area called Avda Regio, part of Aphrodite on Venus, connected by all these deep, deep canyon systems, perhaps like mid-ocean ridges, or I'm sorry, mid-ocean trenches. But again, we don't know, because the scales we see are inadequate to resolve that. There are measurements of the Venus atmosphere measuring the isotopes of hydrogen that suggest Venus once had global oceans that would have filled all these low blue areas, oceans of water. That's a possibility. If it did, Venus may have been a habitable planet. In fact, early in the history of our sun, some scientists think the sun was less luminous, a little less hot. It sort of flares for a while, cools down, and then it, well, eventually dies. That Venus would have been right in the habitable zone. Imagine that. Two big rocky planets with oceans in the habitable zone. One went one way, the other went the other. So as we look at the Venus atmosphere and the Earth atmosphere, we're reminded that there's a lot of the story at scales that we people need to get our grips on. So this is an artist rendering, because we don't have any data, of what the hilly ridge plains of Venus, these areas we call tessera, might look like. There's even new data suggests Venus may be erupting today, like the volcanoes on Earth, like the ones at Eyjafjallajökull in Iceland or other places. This is a possibility. Again, without robotic remote sensing, understanding what these weird landscapes, here's a giant impact crater on Venus, this is the spiderweb terrain. Understanding all this stuff is hard. I mean, if I showed you those maps and pictures made by landers that look like this, you can recognize the Russian writing on those landers, you'd wonder. In fact, the longest surface operation on the planet Venus in the history of humans that made this image was for roughly 2 hours. So imagine having to do all your work, whatever you're doing, in 2 hours. It's kind of like a sprint. Here you see the lander view from the Soviet missions in 1982, CCCP, USSR, lens cap, of course it fell off, good thing, and the view from the other one. So this is our complete data set. You've just seen it in 10 seconds of the surface imaging of the planet Venus. In contrast, for Mars, we have a terabit of images from the rovers and other things. So let me stop for a minute and just put it in perspective. Biggest other planet in our solar system that's rocky, Venus. Jupiter's a gas giant, of course, Saturn, and others. We know less than we did in perspective about Venus than we did about the Earth probably in the 1940s. So in the space age of the last 51 years, we haven't filled in the textbooks on Venus. Who knows what it might tell us about how our own climate system works. So here's Earth, large climate system recorded in the atmosphere. This is from a shuttle flight, and you can see our moon. Now, one of the things interesting about the Earth is we have a very large natural satellite. Now, a generation ago, when I was younger than you guys, we actually sent multiple human voyages to the moon. And you might say, why did we do that? It was brash, brave, bold. We went to the moon because, in fact, it was better for us to develop the systems for people to go fly to the moon in command service modules with capsules than robotically. We actually, those days, did not have the robotic capabilities to do what we do today. You guys have grown up in a generation of robotic IT infrastructure. When we went to the moon and saw landscapes like this, from the field of view you'd see flying over, we went with human eyes the first time in December 1968. So the Apollo program took us to the moon. And you might say, well, you know, what did that do for me? Well, aside from Tang and Teflon, what it did do for the United States was develop not only precision navigation, which we use now, been mapped into GPS, but it also developed the first large-scale integrated circuits, which we needed to go to the moon. Here you see Buzz Aldrin coming off the lander on the first visit to the moon on Apollo 11. We, of course, erected aluminum guy wire flags. It was a big engineering challenge to do that, by the way. We developed the highest land speed cars on another surface, the lunar roving vehicles. And we went to the moon and brought back a legacy of a history of another world in 890 pounds of rocks. We actually set amazing speed records with these things they drove. We left our name tags on there. There's John Young's Apollo 16 mission. This is the legacy of human exploration. In the first decade of NASA, we not only built weather satellites, started missions to explore the outer solar system, but we sent people to another planet. Now, how many of you realize the last time any women or men ever left the protective magnetosheath of our planet was 1972 on these missions? Now, let me stop here. This is a famous picture. In November of 1969, the second of the Apollo surface missions, Apollo 12, Commander Alan Bean went and sampled the lens of a robot we had sent to the moon 3 years before. You might say, okay, sounds pretty cool. He actually landed about 180 meters from, with his lander craft, the LEM as it was called, 180 meters from that, across a distance in space of 400,000 kilometers. Now, do a little math, pretty good navigation to go that far in deep space and land that far. We were then in a missile race. Apply that to the missile race of the late 60s. I think you can all do the math. This was one of the greatest technology feats in the history of the 20th century. Precision navigation on another planet across the abyss of deep space. We actually discovered that the lens of that vehicle had been contaminated with a type of bacteria that survived 3 years in deep space, no air, water, deep space radiation, solar flares, came back, put it in a petri dish, cultured it, grew. So life is tenacious. And we worry about that as we explore planets where we're asking, are they alive? What if we bring ourselves to those planets and then we discover that we're there? Okay, that's a great result. So as we think about astrobiology, where life works, even on the moon, an absolutely airless world throughout its history, we brought life there, not only us in Commander Bean, but in others. So this was a major thing. This is my favorite picture of the moon. This is 6 kilometers looking back at the spacecraft that carried Apollo 17 to the moon across the hills of Taurus Littrow. That was the walk-back distance. If all had gone bad, the guys had to walk back that far to get home. Of course, we drove around, we sampled rocks, we did a lot of geology. I'm a geologist. This is really significant to me. One thing we learned about the moon, it's old. The first rocks told us, famous picture, that when we look at the moon, we're looking at a surface that's frozen in time. It's a fossil planet. Everything you see, including the seismic network we stood up, is recording a history of something like 3.7, 3.8 billion years. How many rocks have any of you seen that are that old? None. The first billion years of Earth history has been wiped. So the attic of the Earth is recorded in the story on the moon. And that told us a lot about ourselves. Here's a famous picture as we left the moon for the last time, coming home to the Earth. So that's the last time people have gone into deep space. That's a bold thing. Now, this is what it looked like landing. Of course, you've all heard the story of what Neil Armstrong had to do to free fly his vehicle. I love to show the drive. The land speed record here was about 16 kilometers an hour. Just for scale, the Mars exploration rovers move about a 50th of that in their speed. So these guys were trucking. They actually had to build new hubcaps a couple times because they went a little fast. But again, it was really a great way to explore. In their trips, and you see how rocky and bumpy it was going along the moon, they actually covered on one mission in Apollo 17, 27 kilometers. Now, stop here for a minute. 27 kilometers in one 7-hour extravehicular activity event. Have we gone 27 kilometers on Mars with the Mars exploration rovers yet? No. And we've been driving for 5.5 years. So, one day, 27 kilometers. Out, back, collect the rocks, come back. We people like to explore fast, particularly in tough places. This is the now, why me generation. That's important. When you move things to the robotic time space, you can freeze time. You can move more slowly. And so one of the things we do in exploring planets and the deep sea floor is we change the time scale. So if it takes a week for a rover to go 100 yards, well, too bad. We'll wait. The robot is doing the job.